All right. Chase is not here yet, so we got to get somebody else to get going here. So like I mentioned, we're going to do the segue into the Calc 3 as to why you need this stuff at all. So let me start by reminding you, the generic form that you've always worked with a conic now, whether you put the constant on the left or the right is kind of irrelevant. Now, this stuff here only has to do with shifting, right? Left, right, up, down. It doesn't have anything to do with what it is. What it is this, right? If I have a sum of squares, I know it's an ellipse. If they're the same coefficient, it's a circle. A difference of squares is going to be a hyperbola. If A or B is 0, then it's a parabola. Piece of cake. But in reality, that's not what you're always going to see. And in fact, in Calc 3, you're almost never going to see it like that. Instead, no, you change it completely. We throw in this term. And we say this, plus EY, there we go. This is the most general form of a conic. And if the B is not 0, that means you have a rotation of axes. That means think straight up and now tilt your axes, maybe your parabola goes this way, or maybe your ellipse goes this way, or something like that. I'll give you the simplest example you already know. I mean, we know this one. This is a very happy one, right? We know this one inside and out. What actually is that shape? Turn your head 45 degrees.
Rotated hyperbola.
It's a
rotated hyperbola.
It's a rotated hyperbola. Oh. In fact, how about if I wrote it this way? 0x squared plus xy plus 0y squared plus 0x plus 0y minus 1 equals 0. It's kind of boring, I know. That's the same thing, isn't it? That's xy equal to 1. xy equals to 1 is y equal to 1 over x. This is a rotated hyperbola. It's rotated exactly 45 degrees. And so if you looked at it this way, right, these are actually my axes. You could think of this as being vertical or horizontal because of the 45 degrees, but it's clearly a hyperbola. So the question is, how do I get from something that looks like that into something more recognizable? Because if I have an xy term, I can't easily tell what the shape looks like. In fact, it might not even be easy to tell what the shape is, but we're going to show that part also. So it's this. It turns out, and I'm not going to go through the formal proof of this because most of this actually comes from next semester. The algebra to prove what I'm going to do is really, really menacing. I was actually looking at it before class. I thought I might do it and I realized it'll take about 4 boards. And when I do the proof next semester, it will take like, this much space. It's really, really quite simple. I'm going to give you a hint. The reason we're doing this now is because next semester it's simply this. I replace the 0 with the third variable. Now, that third variable can equal 0, or it can be something else. So we've talked about this before. For example, the paraboloid, if I slice it, I see a circle. I might see an ellipse. I can take a slice of a shape and see a parabola. I can see an ellipse. I can see a hyperbola. I can see a circle. Piece of cake. But it's the 3-dimensional shape we're actually going to be working with. So we simply replace the 0 with the third variable. And that's what we have to know inside and out next semester. But I can't know that next semester if I don't know what the 2-dimensional conics look like this semester. So that's why we review it now. It actually would make more sense to actually do this right before we need it in 3D. Because there's so many other topics, we really can't afford the extra time it would take. So in Calc 3, it's pretty much always going to be one of these. Because you're in 3D, right? You can have a shape out here in 3 dimensions. It's not a big deal, but to be able to identify what it is really the critical part. So we're going to mess around with this. Now the first thing is, and actually the most important thing, the single most important thing is the easiest thing. Identifying what it is. There are 3 things that are going to go on here. the identification of what it is, calculating the angle of rotation, and then rewriting it in new coordinates that look like, you know, comfortable coordinates with the rotated axes. In other words, we have to do kind of a change of variable. That's the most complicated and the longest part. That's the part most people spend all of their time on, and it actually is the least important part. The number one thing is the identification. And a lot of textbooks actually get this part wrong, which is unfortunate because it's like they don't understand where it comes from. The identification comes from something you're going to learn next semester called a Hessian. Don't worry about that now, right? It's a vocab word that you're going to see next semester. And if you're an engineer, you work with those things in higher dimensions and they can be kind of gnarly. But really it comes down to this: 4ac minus b squared. Right? Only these three things have to do with what it is. The rest of this has to do with the shift, left, right, up, down. If I just simply lopped all of this stuff off, that would mean I'm starting from the origin. If it's a parabola, I'm centered at the origin if it's an ellipse or a hyperbola. That makes life easy, but that's not necessary. So this has three possibilities. It's greater than 0, it equals 0, it's less than 0. Okay? If it's greater than 0, you have an ellipse. If it equals 0, you have a parabola. If it's less than 0, you have a hyperbola. This is the easiest part of any problem you'll run into. Okay? So one of the ways to recognize a hyperbola, for example, if A and C are opposite signs, it doesn't even matter what B is. Okay? If A and C are opposite signs, it's going to be a hyperbola. Turns out you get a hyperbola often. So the B term ends up being kind of important. So I'm going to give you a simple problem. All right? Let's keep it really easy. So I have 2x squared plus 3xy plus 2y squared minus 6x plus 3y minus 8 equals 0. Okay. I have 2x squared plus 4xy plus 2y squared minus 6x plus 3y minus 8 equals 0. I have 2x squared plus 5xy plus 2y squared minus 6x plus 3y minus 8 equals 0. All right, these are three different shapes. In fact, they are extremely different shapes. There is nothing that's even a little bit similar about them. And you're looking at that going, didn't I just write the same equation 3 times? Pretty close. How could they possibly be three different shapes?
Well, the 3, 4, and 5xy.
That subtle change I made.
They're ellipse, parabola, hyperbola.
And how did you get that? Back up one step.
4ac, right?
So here, 4 times 2 times 2 minus 3 squared is what? 7. Here, 4 times 2 times 2 minus 4 squared is 0. Here, 4 times 2 times 2 minus 5 squared is -9. Oh my goodness. First one's an ellipse, the second one's a parabola, the third one's a hyperbola. That is the most important part. The fact that it's rotated, okay, that makes it interesting, but it doesn't make it impossible. But if I don't know what it is, then at the end of the line, I might not make correct conclusions. So the easiest part is the what is it part. Okay? You like that because that's just not a challenge. So right off the bat, wait a minute, what if I multiplied both sides of the equation by -1 and I changed all of the signs? If I changed all of the signs, then A, B, and C would all be the opposite signs, but would this value change? If A and C if I changed the sign on both A and C, wouldn't 4AC still be the same value? And wouldn't B squared still be the same value? If I multiply both sides by 10, it won't be the same value, but I'll still have the same sign. Because I'm just multiplying a positive or a negative number or 0 by that value, in other words. So that's key. You want to have that written down somewhere. Some textbooks actually have this backwards, which is, it's unfortunate that they have it backwards. In fact, some textbooks actually give it the wrong name, which is even weirder. No, the farther you go in math, you'll see this in this type of math over and over and over again. So number one is identification. Second thing is we're going to figure out the angle of rotation. So now I'm going to back up and we're going to set things up. Okay, so give myself a little picture so I always make sure I got everything in the right place. I need many, many colors here. All right, so I've got a point. Okay, pretty exciting. I have a point. Multiple colors here. Now, I'm going to rotate the axes. I'm going to draw, here's my new axes. Okay, we'll call this the x prime and y prime axis. Gotta give it a name. These are my new axes. They've been rotated, and the angle we're going to rotate them is the angle phi. People get these things confused all the time. A lot of us are really lazy when we do these and we kind of make our little slash maybe diagonal. You kind of need to be really specific. Do you use this very often? In Calc 3 you use this always. But you use it for a different reason in Calc 3. For right now we're just coming up with a different angle. But this one is used just as often as this one is in Calc 3. So try to make them not look exactly the same. So the angle phi, now, that's the angle of rotation, but there's still an angle here. So let's call this angle theta. Okay? So let's start with that. Now, so if I'm looking at this picture right now, okay, if I'm looking at this picture right now, then it's pretty clear. Oh, let me give this a name. We'll call this length R. A little bit later, in a few days, we're going to introduce polar coordinates and things like that. And a lot of you remember polar, a little bit about it. Polar coordinates, it always has to do with the distance from a point, the point is to the origin, that we always call R. Like as in radius of a circle kind of R. Okay? So in my picture, it's not all that exciting. So now what I need to do is I need to go, I'm going to make this a little longer. Oops. I need to do this, okay, and then I need to do this. Make my right angles there and there. So let's use a little bit of trig, okay? Just a little bit of trig right here. Let's start with the x prime, right? Think SOHCAHTOA. So what do I know right there? Well, this coordinate now, we called it xy in the regular xy plane, but we're also going to call it x prime y prime in the x prime y prime plane. Why? Because I went out, that's x prime units right there. And right here, right, that's y prime units in that direction, x prime units in that direction. Now x prime does not equal x, y prime does not equal y necessarily, but that's the point. So what does x prime then equal? Well, looking at this picture, it should equal r cos theta. And what does y prime equal in my picture? In SOHCAHTOA? R sine theta. Yeah, that's not real complicated. Okay? Again, because the cosine, right, ca, it's this divided by this, and the sine would be this divided by this, and that's exactly what I got. Okay, so that's the easy part. Now, let's consider that big old humongous angle right there. And let's do SOHCAHTOA for xy. So there's my angle. So x should be r cosine of theta plus phi. Agreed? Y should be r sine of theta plus phi. Let me get rid of all this other stuff here. Now we have, I call them the alpha beta identities, just to remind us in case we forgot. Do you remember either one of these?
Yeah.
Most people remember the cosine betas. Cos minus sine sine. You guys remember that one? So this would be what? Cos alpha, cos beta, minus or plus, sine alpha, sine beta. And what would this one be?
Sine alpha, cosine beta, plus or minus.
The same.
Yeah. Cosine beta, cosine alpha, sine beta.
Yeah, because it's a, it doesn't matter what order you write those in, as long as you switch. Okay? Keeping that in mind, let's do exactly that. So this would be r cos theta cos phi minus r sine theta sine phi. This would be r sine theta cos phi plus r cos theta sine phi. Making sure my thetas and my phis don't look the same. Okay. Do you notice anything? Oh, so that means this is what? X prime cosine phi minus y prime sine phi. How about over here? Y prime, X prime, I'm going to put the X prime first. It just makes it a little bit easier to remember. So sine phi plus Y prime cos phi. So the first thing is when I do a rotation of axes, I don't know the value of phi. We're going to figure that out. We have to find the value of phi. But this I absolutely know. X is the rotated axis in this way. And notice that the theta doesn't actually figure in, does it? Only the phi does, because phi was my angle of rotation. So I get this. This is huge, okay? We get this part here, and that now tells us we have to figure out the sine of theta and cosine theta. Or, I'm sorry, sine of phi and cos phi. We don't necessarily need to know the value of phi. What we really need is the sine of phi and the cosine of phi. If phi ends up being a common angle, yeah, we'll find it. But if phi is not a common angle, but I know the cosine of phi and the sine of phi, if I know what those numbers are, that's actually more useful in the long run. So, now we're going to do the icky part. All right, we're going to start with our equation. Now here's what I'm maintaining. Only the second degree terms contribute to the angle of rotation. The other ones are a vertical or a horizontal shift. It has nothing to do with the angle. So the only parts we actually need to substitute are the first three terms, okay? It won't change anything if I do the last terms. So we're gonna look at just the first three terms, and what we're gonna substitute are these two quantities, okay? And this is where it gets kind of ugly. So, if I rewrite this, this is A times X prime cos phi minus Y prime sine phi squared plus B X prime cos phi minus Y prime sine phi times X prime sine phi plus Y prime cos phi, and then plus C times X prime sine phi plus Y prime cos phi quantity squared. This is the only part I need. Now we're going to expand, we're going to gather terms, and then we're going to manipulate. So the expansion, I got to square things. It's not that complicated. It's tedious, but it's not complicated. So here, what do I got? I have A times X prime squared cos squared phi minus 2a x prime y prime cos phi sine phi plus a y prime squared sine squared phi. Did I get that right? So that's one minus 2 of those plus the last one. Yeah, I think we got it. Now here, plus, just going to distribute, b x prime squared cos phi sine phi, and then the outer ones, plus b x prime y prime cos squared phi, now the inner ones, minus b x prime y prime sine squared phi, and then the last ones, minus b y prime squared. It's sine cos, but we wrote cosine here, so I'll continue writing cosine. It's easier to keep track of the terms. Cos phi sine phi. Okay. And let's see, do we got that one? Double check. Cosine, cos squared, sine squared, and then cosine again. Yes, okay. And now the last one, plus c x prime squared sine squared phi plus 2 c x prime y prime cos phi sine phi, and then the last term plus c y prime squared cos squared phi. Okay, there's a lot of stuff going on here. But the only stuff I truly care about, believe it or not, are the b terms. And here's why. If I gave you a conic that had an x squared and a y squared, but no xy term, if there's no xy term, there's no angle of rotation. It's a happy graph that you already know how to do. That's what we've been doing, okay? If I give you a conic and there is an xy term, that coefficient, we call it b. When I do my angle of rotation into my new set of axes, x prime, y prime, I'm rotating it so the original will have an ugly equation, but the rotated will have a happy equation. Does everybody understand what I mean? I'm going to rotate it, and now it's going to be a happy looking parabola or ellipse or hyperbole equation. Meaning, if I think about my rotated equation, call it x, a prime, b prime, c prime. I need the new b to be 0. When I rotate my axes, I need the new xy coefficient to be a 0. Otherwise, I have just as ugly an equation as I had before. So the only things we need to look at here, right, are the x, not, I'm sorry, I said the b terms. I'm sorry, the x prime, y prime terms are the only terms that I need to manipulate. So let's gather all the x prime, y prime terms. Okay, I think I got that. Does that look right? X prime, y prime.
Is there another one
Is
right
there
next
one more?
to the
Oh,
middle one?
There's one. Thank you. There's one more here. I think that's all. Is that right? So let's put all those together. So I'm going to have negative 2a cos phi sine phi plus b cos squared phi minus b sine squared phi, and then the last one would be plus 2c cos phi sine phi, and all of that would be multiplied by the x prime y prime. That's the coefficient of the x prime y prime. I don't care about the other ones. I only care about this one because I need that coefficient to equal 0. Well, that's kind of scary looking at the moment, but you know, how about if I put these two together? If I put these, the first and last one together, that will look like what? 2c minus a times cos phi sine phi, and then these two together, hold on, those are both b's, right? So plus b times cos squared phi minus sine squared phi. There we go. Remember, I need this whole thing to now equal 0. but I see something in here. Maybe you guys notice this.
Trig identity.
Yeah, what is that guy right there? That's the double angle. That's cosine of 2 phi. Gee, wouldn't it be convenient if the other side also had a double angle formula?
Sine.
You see it?
Yeah.
Isn't that sine of 2
2.
phi? Ooh. So now I have c minus a sine of 2 phi. And that whole thing equals 0. Lost my b here.
Is
There
it
we
also
go.
still all multiplied by x prime, y prime?
Well, no, we're setting the
Okay.
coefficient equal to 0.
Okay.
So we were just figuring out the coefficient, and now, so if that equals 0, then is it safe to say, if I throw that guy on the other side, that b cos 2 phi equals a minus c sine 2 phi? Do you agree with that? So that leads to a very nice equation. I can throw this over and throw that over. I could get b over a minus c equals sine over cosine or tangent. Or I could do it the other way and say a minus c over b equals the cotangent. Which one would we rather have, by the way? No brainer. We'd rather have the tangent, wouldn't we?
Yeah.
Except that leads to a problem. B is not 0. The reason you're doing this is because you had a B, remember? That was the whole point. But can A and C be the same thing? Yeah, they'll often be the same thing, which means the one on the left is actually not going to work so well. Ah, darn. And it also leads to a different problem. When I do a rotation of axes, the most phi could be would be 90 degrees. Because if I rotated 90 degrees, I really didn't rotate at all. I just kind of swapped x and y. You know, if I take a parabola and I turn it on its side, don't I just write that now as x equal y squared? Oh, if I took the ellipse that opens vertically and turn it on its side, now you guys understand that that's not really a rotation of axes. So we'd say the most phi can be. I'll use degrees. Therefore, tell me about 2 phi. Two phi can be anything from 0 to 180. And here's the nice thing. Cotangent of 0 is undefined. Cotangent of 180 is undefined. But everything in between is fine. But the problem is the tangent function's undefined at 90 degrees, which would be a phi of 45 degrees. Oh, so a 45-degree rotation means the tangent's impossible. So as much as we hate working with cotangent, folks, this is the formula we have to use, because this one can get us in trouble. It doesn't always work, okay? So this is how we determine the angle of rotation. Wait a minute, but I don't have to do any work. If I gave you the original problem in this form, a minus c divided by b, that's all I have to do, and then that's the cotangent. Yeah, but it's the cotangent of 2 phi, so I have to kind of work backwards to figure out what phi would be. But that's actually not very hard. We're going to do a problem. I'm going to show you that part. That's actually fairly simple to work backwards. So I can now tell you. Now, by the way, let's assume that A is not equal to C. Because if A equals C, then you have a 45-degree rotation. Okay? How do I know? Because the cotangent of 90 degrees is 0. That would mean phi is 45 degrees. This one we usually, you can give radian answers. But because your angles are not always going to be nice, sometimes it's easier to give a degree answer because it's easier to conceptualize. If A and C are not the same thing and I want to find the angle of rotation, I can do this and just hit the inverse on my calculator. That's actually a really simple thing to do, right? Because cotangent is just the reciprocal. So if you actually wanted to tell me the exact angle of rotation, even in decimal form, this would actually be pretty easy, okay? So second thing is angle of rotation. But again, I haven't really done any work. I just picked off 3 coefficients. The angle has nothing to do with left, right, up, down, shifting something again. That only has to do with turning the axes. So now let's do a problem from beginning to end where we actually are doing this and substituting and all that stuff so you can see how this works in general, okay? What we're going to do next is the most algebraic part, but as it turns out, it's not the most important part. The most important part is the easiest part, the identification. Okay, so what problem did I choose? Oh, I chose something really ugly. All right, this is nice. So. All right. Well, first things first. What is it? Anybody tell me what it is? It's a parabola because 4ac minus b squared turns out to be 0. Okay. Boy, that sure doesn't look like a parabola, does it?
No.
If I increased this a little bit, it would have been a hyperbola. If I decreased this a little bit, it would have been an ellipse. But this one's a parabola. Okay. Now, the reason that's important that I do that is at the very end of the problem, when we're all done and we've got this new equation in x prime, y prime world, it ought to look like a parabola. Because if it doesn't look like a parabola, it probably means we made an arithmetic error somewhere. So, we're going to do that next. Okay? So, a minus c, what's a minus c? So it'd be 16 minus 9, and that's over 24, or 7/24 equals the cotangent of 2 feet. With tangent and cotangent, we usually like saying 1s, or root 3s, or 1 over root 3, right? Those are the common ratios from common angles. Is that a common ratio for anything, Triggish? No. Which means that the actual angle is going to be something probably ugly. But it's not the angle we need the sine and cosine of the angle, and that might actually turn out to be very nice. So let's do that. Now I'm going to show you how to figure it out, and we actually have to use the double angle formulas. So, quick reminder, right? We know this. Right, every trig, every pre-calc, every calculus book has this probably on the back cover. We do 3 versions because which one are you going to use? So if I put these two together, then the cos squared of theta is 1/2 of 1 plus cosine of 2 theta. If I put the first and last together, then the sine squared of theta is 1/2 of 1 minus cosine of 2 theta. Now you've all used these because if I had to integrate either of these, I can't. I end up working with these guys. But we're going to use these in reverse. Because theta has to be between 0 and 90 degrees. No matter what, theta has to be between 0 and 90 degrees. That means the cosine and sine of theta are both positive because you're in the first quadrant. Is that important? Yeah, because I need to do the square root. So in other words, cos theta then will be the square root of 1/2 of 1 plus cosine of 2 theta. And the sine of theta will be the square root of 1/2 of 1 minus cosine of 2 theta. If I didn't know, I'd have to throw a plus or minus, and then that would be kind of wonky because then it feels like I'd have 2 sets of equations. But because theta is is between 0 and 90, you're in the first quadrant, automatically these are both positive. Okay, that helps me a lot. So how does that help me here? Well, can you draw me a picture in the first quadrant? That's a feet. Can you draw me a picture in the first quadrant where the cotangent of this angle is 7/24? Let's see. Tangent is this over this, so cotangent is this over this. Okay. What goes here?
25.
25? How'd you get that?
Root of 7 squared plus
Pythagorean theorem, right? Like, oh yeah, we have that thing. Is that a nice number? Yeah, it's not a root. Oh, that's a very nice number. Can you now tell me what is the cosine of 2 phi? What is the cosine of 2 phi? Are you calculating it? Come on, guys. If you're calculating it, then you're doing something really strange. It has nothing to do with the question. Your angle is 2 phi. What's the cosine? This over this. I need the cosine. Oh, how am I going to do that? Right here. So now what is the cosine of phi? It's going to be 1/2 of 1 plus 7 over 25 all under the square root. Gosh, that's scary looking. Use your calculator if you have to. Well, let's see. 1 plus 7 over 25, that'd be 32 over 25. And half of that would be 16 over 25, and the square root of that is just 4/5. Ooh, well, that's kind of nice. How about the sine of phi? Well, that should be 1/2 of 1 minus 7 over 25. Would that be 25 minus 7, or 18 over 25? Half of that's 9 over 25, and the square of that is 3/5. Oh, it's a 3, 4, 5 right triangle, isn't it? Have we calculated the value of phi yet? No, but you could tell me. What's the value of phi approximately? In degrees, phi is about 36.87 degrees. I just did inverse cosine of 4/5. Is that a common angle? No. But I could probably, draw a picture relatively soon, or relatively simply. These are the values I need because when we do our substitution, the x prime, y prime, I'm going to use these where you saw a cos and a sine phi. Okay? So what does that give us then for this problem? That gives us very specifically what? That our x, we're going to substitute x as what? So what was x? I'm sure we did that. Yeah, we already did that. So x is x prime cos minus y prime times sine. And what's y? X prime times sine plus y prime times cos. Ooh, there's no roots in there. It's kind of nice. So I'm going to replace the x's and y's with this. Now I'm going to show you a little trick that I do because I'm really lazy. Do you really want to be taking all these fractions and raising them to powers and multiplying all these fractions together and keeping track of all the terms? Does everybody realize that could get you in a little bit of trouble? Because it's kind of messy. So I have a lazier way. I want to get the right answer. I want to avoid some of the pain and suffering. So how about if I rewrite this as 1/5 of 4x prime minus 3y prime, and I write this one as 1/5 3x prime plus 4y prime. Is it the same thing?
Mm-hmm.
Yeah, but now I will avoid all the icky fractions when I'm doing the manipulation. I'll just have one fraction in front. See, that's what I do. I'm lazy. I'm going to get the same answer, but I'm going to do it in probably 1/5 of the steps as anyone else, and I won't have any arithmetic errors. Everyone else will have lots of arithmetic errors because they're trying to manipulate fraction, multiplication, sums, different denominators. Yuck. Nah, just factor it out. If these were roots, factor out the root. It's easier. All right, so now let's go to here. So I'm going to have 16 times 1/5 4x prime minus 3y prime squared plus 24 times 1/5 of 4x prime minus 3y prime times 1/5 of 3x prime plus 4y prime I don't need this right here. Plus 9 times 1/5 3x prime plus 4y prime quantity squared minus 60 times 1/5 of 4x prime minus 3y prime, minus 80 times 1/5 3x prime plus 4y prime, and then finally plus 100 equals 0. I think we got that. Now, this stuff will only have to do with the shifting, right? Left, right, up, down. The other stuff, now, if I did this correctly, if I have no errors, then the coefficient of the x prime, y prime should be 0. Everything should cancel. If it doesn't cancel, don't force it. Go back and find the error and fix it. It's really easy to make an error, obviously, because we have so much arithmetic going on. So, I got a square of 1/5, that's 1/25. So how about if I write this as 16/25, and now times 16x prime squared minus 24x prime y prime plus 9y prime squared. I'll distribute that in a moment. So plus 24 over 25 times 12x prime squared plus 16 minus 9, so plus 7x prime y prime, and then finishing off with minus 12 y prime squared. You notice I'm not manipulating any fractions. I put them outside. A fifth squared, so oops, plus 9 over 25 times 9 times x prime squared plus 24 x prime y prime. I don't do this anymore. Plus 16 y prime squared minus 12 times 4x prime minus 3y prime minus 16 times 3x prime plus 4y prime plus 100 equals 0. All right, now let's distribute our coefficients, and then basically that's pretty much the last of the algebra. All right, so we got here 256 over 25 x prime squared. And what's this going to be? Minus 384 over 25 x prime y prime, and plus 144 over 25 y prime squared, plus 288 over 25 x prime squared, plus, what do we got? 168 over 25 x prime y prime, minus 288 over 25 y prime squared, plus 81 over 25 x prime squared, plus 216 over 25 x prime y prime, plus 144 over 25 y prime squared, minus 48 x prime plus 36 y prime, minus 48 x prime, and then where are we here? Minus 64 y prime plus 100 equals 0. All right, let's start by gathering the x squared terms, or x, I should say x prime squared terms. All right, so I'm just adding coefficients. Okay, can you add those coefficients for me?
625
Over,
25.
huh, that's convenient. What's that?
5, right? I think.
625 over 25 is?
25.
25. Oh, so CC says that one's 25 exactly. Who knew? Okay. Let's gather the x prime, excuse me, x prime y primes. Do I have all of them there? Yes, I do. Okay, so negative 384 over 25, plus 168 over 25, plus 216 over 25, and that adds up to?
0.
0. Is that a good thing? That's a good thing. You know what that means? We did it right. If that doesn't add up to 0, it means we didn't do it right. Please do not automatically cancel things, because you might have distributed badly. Something wonky could have taken place. Finally, let's add the y prime squared terms. So 144 of them plus 144 of them minus 288 of them, that's
0.
also 0. Oh, I'm going to have an x squared but not a y squared because this is supposed to be a
Parabola.
parabola. Does that make sense why that would be 0? Yeah, I can't have both of them be squared. Wow, everything's canceling. All right, next, how about the x prime?
Negative 96x.
How about the y prime?
Negative.
If I didn't mess that up, would that be negative? Is that right? Negative 28?
Yeah.
Plus 36. Yeah, I think that's right. So you said negative 28 y prime, and then finally plus 100 equals 0. Now, this is a parabola. If we don't have any errors in the coefficients, and I sure hope we don't have any errors in the coefficients, wouldn't you rather write it as y prime equals?
Yeah.
It's a parabola. So how about, throw that guy, in fact, let me do this. I'm going to be lazy. If this were an unrotated thing that looked like 25x squared minus 96x minus 28y plus 100 equals 0, if that's what we were actually working with, wouldn't you rewrite this as 28y equals 25x squared minus 96x plus 100? You with me so far?
Yeah.
Yes, I can divide through. That would be correct. Might be easier to complete the square though. It might not be. That's pretty ugly numbers, isn't it? Is it really 96 and 28? Yeah. Okay. So if I just do this, 96 over 28, I won't bother reducing yet, and then something tells me we might have is there an arithmetic error over here? All the other numbers worked out so beautifully. It's strange that this one is so ugly. I'm sure I actually I took a problem from a textbook, so hopefully I wrote it down correctly. Minus 60, minus 80, no, that's right. Minus 60x, minus 80y. No, that is correct. Ah, those are just ugly numbers. Now, can you tell me the axis of symmetry in the vertex? Yes, you can. Looking still in this form, isn't the axis negative b over 2a? And what does that simplify to? So what is that? Negative 48 over 25? Very close to negative 2, in other words. Now, somebody with your calculator, put that in here. It's ugly, I know. So what will your y coordinate be when you do all that? Turns out it's actually kind of nice. I just did it on my calculator. You get 7 over 25?
I'm checking.
Didn't get an icky decimal, in other words. So that means I can rewrite this as y equals 25 over 28 times x minus the x coordinate okay, so let's go back to here. That means I can rewrite this as y prime equals 25 over 28 times x prime plus 48 over 25 plus 7 over 25. This is our rotated equation. We're actually going to attempt to draw this. I said it's long, it's tedious, there's no part of this process that's difficult. I mean, we're multiplying polynomial-ish things. So, what did we say the angle of rotation was about? You did the inverse cosine of 4/5, and what did you get? About what? Do we lose something?
36.8 degrees.
Yeah.
Oh, did I? Oh, you're right. You're right. Oh, boy. Oh, you're right. I did not see that. So it's the negative. This should be positive, shouldn't it?
Yeah.
So that changes this, doesn't it?
Yeah.
What does it change it to? She's right. That should have been a positive. Oops. So let's resubmit that guy. That does matter. Actually, you know what?
Still 7, I think.
Yeah, I think when I actually entered it, I did do it as a positive. Because I had done it earlier to see that it worked. Yeah, so actually that is correct. It is still 7. But this is a minus rather than a plus. And that definitely changes where the vertex is. This is still 7. Okay, so what is our angle of rotation in degrees, somebody? Inverse cosine of 4/5 is about what?
36.8 degrees, something.
About 36.8 degrees. I'm just gonna eye shot it. 40 flats, a little less than 45, maybe. Yeah, that's pretty close, right? Okay. So here's what you're doing. You're tilting your head now. You're going like this. So on this set of axes, almost 2 units, small. So 1 unit, 2 unit. Okay, so I'm about maybe here. That's a little less than 1. So it's pretty close to a y equal x squared kind of shape. Does everybody agree with that? Now, that value there, it's about 3.5. So 0, 3.5 roughly is my y-intercept. Again, we're freehanding this. That's probably about there. So, there. That's what it looks like. It's that parabola rotated 37 degrees. Now, the most important thing about all this was it's a parabola. That's actually A number 1. Being able to determine what it looks like is useful because what's going to happen later, I might have intersections of shapes. Or I might have a 3-dimensional shape and I need to compute the volume or the surface area or something. I have to have a reasonable idea of what it looks like. You're never going to draw one. I'm drawing it so you know what we just did. So I took something absolutely hideous and scary. We figured out what it was, we figured out the angle of rotation. By the way, did we ever actually use the angle itself? No, we used the sine and the cosine of the angle. If the angle of rotation ends up being nice and being a common angle, like 45 degrees or something, then wouldn't the sines and cosines have been irrational? And that would have made all of this actually probably more work, not less work. But because sine and cosine ended up being rational, that made the algebra of this, and not easy, but certainly not nearly as awful. So, I'm going to ask you a quiz next week, and I'm going to give you some shapes and say, what is it? What's the angle of rotation? And that's most of it. Most people would say, all of this was to get this. I've taught Calc 3 100 times. Do you know how many times you're going to do that in Calc 3?
Hopefully not very many.
Never. In fact, after this section, you know how many times you're going to do it? If you studied math the rest of your life, and how many more times you're going to do that? Never. The thing everyone makes the most important part is actually the least important part. What is it? That's the most important part. I've helped author many calculus books. I've reviewed many. I've been an editor as a student, and I've been a paid reviewer, professional, and you know what? Nobody ever uses this again. Why? Because in 3D, you can't do any of this. This only works in 2 dimensions. You can't have an axis rotated when you're in 3D. You rotate the entire X, Y, Z, but it's a completely different animal, so we don't even worry about it. And so in 3D, we just say, what is it? And as long as I know what it is, everything else just sort of falls into place. So I don't want you to overemphasize. I'd like you to be able to do this because the algebra is right there. But what is it? The angle of rotation, main things. And those things should be relatively simple. Okay? Any question on this? All right, we're now done with everything conics. Now we're going to move on to the next thing, which is, again, another segue into Calc 3 stuff. And that is what are called parametric equations. So let me do a little background. Parametric equations. It sounds kind of scary. The word parameter, depending on the context, is one of those words that has potentially multiple meanings. How many have had Math 119? Okay, what's a parameter in 119? You remember? You only have two. You have parameters and you have statistics.
Oh, it's to do with, population?
Yeah, a parameter is the population variable. A statistic is the sample variables. Okay, so you have mu as your population mean, x bar as your sample mean. A parameter in statistics just refers to a population variable. Nothing to do with this type of parameter. It's one of those words that has multiple meanings, but it's a context thing. Parametric equations have to do with a parameter I like to define as an external variable, a variable that was not part of the problem that helps you describe the problem. Now I'm going to show you something that you may have done in baby algebra. Okay, because it's closer to what we're about to be doing. All right, so you're solving a system of equations, let's say, and you've got and then let's say we have I want to solve this system of equations. Now, there's actually 6 ways I can do it. Some of them involve, matrix algebra and stuff, but that would be overkill. So if you were in a baby algebra class, what would you probably do? You either solve for one of the variables and substitute it into the other, or you line them up and just do elimination by addition, right? Most of us would agree that's probably the easiest one. Okay? So what would I do? Well, maybe how about if I throw the negative 10x on the other side, plus 5y, and I'll throw the 15 on this side, and then I'll have this one. Okay, you with me? So now what would we do? I want to eliminate the y's, so maybe multiply this equation by 2, and this equation by 5. There aren't options. Well, if I multiply by -5, nothing will cancel. So -5 is probably a bad choice. How about 5? Yeah, that would probably make more sense. Yeah, if nothing cancels, then not a good choice. Okay, so when I do that, all right, so now my top equation is -20x plus 10y equals 30, and my bottom equation is positive 20x minus 10y equals, hold on, did I lose a constant somewhere? Oops, hold on a second, I think I lost a number. Hang on a second. Did I just? Oh, my bad, I just realized, this should be a plus 15. Oh, gosh, what was I thinking? That's a plus 15, sorry. Now it's a minus 15, there we go. I gotta fire my editor. There, that should be a minus. And then that works. Okay, great. So then the x's cancel beautifully, and the y's cancel beautifully. And on the other side, the 30s cancel. Everything canceled. Why did everything cancel? There's only one way to explain that. I gave you 2 equations of lines. Any ideas? If I put it in slope-intercept form, this will be y equals what? It would be y equals 2x
It's a scalar multiple.
minus 3. And if I put this one, I throw that over, this one, second one will be y equals 2x minus 3. They are,
Same thing?
they're the same line.
Okay.
Right? I just asked you to solve a system of equations, I gave you the same line, I just wrote it in two different ways. Well, if you have two lines on a plane, what are your possibilities? Do you remember? I have two lines on a plane. This is, again, baby algebra. This isn't high-level stuff. There are three possibilities if I have two lines on a plane. It's the whole point of parametrization. I could have had, you know, that. I could have had that.
And then skewed.
And I could have had that. In other words, unique solution, parallel lines, so we call that an inconsistent system. They never intersect, or I just gave you the same line twice. Call that a dependent system. Now, the first and last one are okay. In the first one I have one solution. How many do I have on the last one? Infinitely many. Ooh, they share an infinite number of ordered pairs. And so it's how do I answer that question?
So then what, like skewed lines are unnecessary?
Well, that's 3D.
Okay.
We're just talking lines on a plane.
Okay.
I'm two-dimensional right now. Yeah, that's different animal. I'm just talking about the parameterization. So I remember my son asked me this question when he was in whatever, Algebra 1, whatever year that was in his life. And he said, I have a problem with the answer in the textbook. I go, why is that? Well, I just figured out it's the same line, but in the book it says there's infinitely many solutions, which is correct. But it kind of sounds like if I said, okay, where do these lines intersect? You said there's infinitely many. Doesn't it sound like we're kind of saying the whole xy plane is the answer?
Mm-hmm.
But it's not. It's just a line on the xy plane. And in fact, next semester when you're working with things like this, I might have a line in space. There's infinitely many points on that line. But that line in space doesn't take up a whole lot of room, does it? So simply to tell you there's infinitely many points doesn't really tell you anything, because you need to know where are these points. It isn't the whole xy plane. It's only the points on the line. But how do you say that? So in a baby algebra class, they'll say things like there's infinitely many points. No, I want an answer that's a little more useful. So we are going to select a parameter, an external variable outside the problem. I usually like using t. That's the most common one. So in this situation, I might say, let's let x equal t. And if x equals t, then what's y? 2t minus 3. So we'd say the solution, we write it like this. This is actually the formal way. The set of, the vertical bar means such that t is a real number, meaning there's no restriction. Often there will be restrictions. There's no restriction. So we're trying to find points of intersection. Look how I wrote my answer. Doesn't my answer look like a point? I mean, it looks like a very specific ordered pair. Now give me a value for t. T is 0. If t is 0, then 0 comma negative 3. Yeah, 0, negative 3 works. How about if t is 1? 1 comma negative 1. Okay, that'll work. How about if t is negative 3? Negative 3 comma negative 9. Yep. Give me any value for t and I will give you the ordered pair that is on the line. The benefit of writing an answer in this form, it now actually looks like a line, but I just told you every single ordered pair on the line. And you said, wouldn't it have been easier just to say the answer is the original line? We can do this in all dimensions though. So we can do this in 3D. This is going to be first day of linear algebra. Okay, you guys all understand you're in the first octant. Did you know that? You're in the first octant of x, y, z space. I know that's kind of trippy. The x-axis is right there, it's coming out of the board. Y-axis is right there, the z-axis is here, and you're positive x, y, z coordinates, so you're in the first octant. Not quadrant, octant, there's 8 of them. So, if I said, here's a wall and the floor, do they intersect? Yeah. Where do they intersect? Along this line. How many points of intersection? Infinitely many. How would I indicate where they are? You'd parameterize. But now you'd have 3 variables. This is how you answer questions in general the higher you go up. Because if the answer is not one specific point, I have to indicate where those infinitely many points are. But this was not really a whole lot of work. This is a parametrization. Okay, that's what this is. Okay? So, there's two ways we do parametrizations. You're given something in XY world and you create the parameter, or you're giving something that's already been parameterized and you work backwards to say where is it in XY world. Does that make sense? So, let me do an example. Here's a good one. I'm going to tell you that x equals, how about 3 times the cosine of t minus 4, and y equals 5 times the sine of t plus 1. And t ranges from 0 to 2 pi only. So t is not all real numbers. Well, what a lot of people do, they'll do this. I'm not a big fan, but this will always work. You remember when you were babies in algebra, how you just made a little XY chart? Remember doing that? Well, guess what goes here? So pick values of t, and now fill in the x and y. That will work slowly. I'm not a big fan of that, but it's still valid. Let's not do that. I would like to be able to write this in XY world. Well, I do have a sine and a cosine in there. What if I isolated the cosine in the first one? So add 4, divide by 3. Then what's the cosine of t equal? X plus 4 over 3. Okay, what's the sine of t equal then? Okay, do we all agree with that? Well, do I try to go x and y and manipulate those? No. Don't we know that the cosine squared of t plus the sine squared of t is 1? But what's the cos squared of t? That would be x plus 4 over 3 quantity squared. And the other guy would be y minus 1 over 5 quantity squared, and that's supposed to equal 1. How about if I wrote it this way instead? Maybe it'd be more obvious. What is it? It's an ellipse. Oh, so I just gave you a parameterized form of the ellipse. Every conic section has very specific ways to parameterize it. And why would I care about doing that? Because right now x and y are both functions of t, aren't they? They're functions of t. Is an ellipse a function? No. I can take anything that is not a function, and if I parameterize it, I can make it functions of the parameter. Why was that a good thing? Because then I can do things like derivatives and integrals and arc lengths and all of the stuff we would do for functions, we can do for parameterized things if my parameterization is good. That's a huge, huge benefit. Okay? And by the way, what we're going to be doing next day are things like derivatives and arc lengths and things like that. We're going to be able to find the arc length of this thing because I can do dx dt. I can do dy dt. I can't do dx dy or dy dx because they're not functions. So one of the huge benefits of parameterization, again, is the calculus of it. I'm not doing the calculus of it yet. We're just doing this part of it. Okay? And then what that will naturally lead into is the very specific parameterization that is polar coordinates. That's a very, very specific type of parameterization. And that turns out to be one of the more important things we're going to do. So let's try another one of these bad boys here. All right? So let's say that x equals root t and y equals t minus 2. I would like this in XY world. And by the way, whenever possible, I'd actually like to draw the graph. So if I said, what is it over here, you'd say it was an ellipse centered where? That would be important. You know, ellipse and give me the center. you don't really need to give me the foci and keep going, but certainly an ellipse and where it's centered would be useful information. What the heck is this thing? Well, what's x squared? T. So this is y equals how about x squared minus 2? Oh, well that's not bad. So that means the graph of this, so it'll start here and then it'll go up. And that's it. Wait a minute, that's not the parabola of y equal x squared minus 2. It's this one. Can t be any real number? No, t can only be
Positive.
not negative. So therefore, can x be any real number? Or can x only be non-negative?
Not negative.
Oh, so there's nothing to the left, is there? I didn't tell you a restriction. I think there's pretty obviously a restriction here because this t can't be negative, and certainly this x cannot be negative, can it? Oh, so I only have to the right side. So if I said, what is this? How would you answer this in words? Because this is important. You'd say the right half of a upwards opening parabola centered at 0, -2. Is that enough information that I would know exactly what this is? Yes. Well, the most important thing was the parabola and the right half. You know, it's a shape. Right? No, it's definitely parabolic because that's the equation of a parabola, but it's not the whole parabola. It's only half of one. But specifically, it's the right side. So there is a restriction. Now let me go back to the first problem. This was clearly an ellipse, and it was very easy to determine. In fact, what was the final equation we got? We got x plus 4 squared over 3 squared plus y minus 1 squared over 5 squared equals 1. This is what we got. So if we were to draw this, again, we would draw it for ourselves. Okay? So 1, 2, 3, 4, 1. So there's my center. I'm going to go up and down 5 units. I'm going to go left and right 3 units. So here, here. And fair, okay, there's my ellipse. How could I have made it different? What if I wanted the top half? Not the whole ellipse. I only want the top half. What do you think? Now let's make sure of one thing. Where am I on this when t is 0? When t is 0, I am where? Well, that would be 3 times 1, so -1, comma 1. -1, comma 1 is right here, by the way. Keep it easy. Now let's pick pi over 2. I'd be at -4, comma 6, which is right here. And when t is pi, that'd be -3 minus 4, so -7, 1, which is right here, and it's going in this direction, isn't it? So if I wanted the top half, it would be 0 to pi. But I should probably check just to make sure it's that. What if I wanted the left half? I wanted the right half. I would just simply restrict the domain. Now, I'm gonna mess with it. I'm gonna change everything. I'm gonna make it this instead. I'm gonna change it to that. Would be the same?
Yeah.
Because I'm still going all the way around, aren't I? In other words, my period is still 2 pi. Oh, so as long as I would, by the way, I would just be starting in a different place. I'd now be starting here and then going all the way around. It's because this is t, this isn't 2t or half t, because this is t, and this goes from 0 to 2 pi, I'm completing everything. Now, what if I put no restriction? What if there's nothing there? then what is the graph? Means you're going around forever and ever and ever and ever. And that's confusing, because if I said, what's the arc length? Would it be one time around, or would it be infinite? You see the ambiguity of that. So generally speaking, a closed shape, you usually give the interval that you're going to use. Right? We don't say t can be any real number. That makes it a little bit confusing. All right, let's keep going. I would like to parameterize this. So what is this? Make sure we all agree. What is this? It's a thing, right? And what kind of thing is it? Yeah, it's a circle. I would like to parameterize this. Whenever you have a conic in general, it's not an absolute rule, but it's just everybody uses the same guidelines. Always pick x to go with the cosine and y to go with the sine. You could still get something if you switch that, but it just generates confusion because polar is always defined that way, that x goes with cosine, y goes with sine. It just makes it a little bit cleaner. So would I say, here's my question, would I say x minus 2 is cosine t? And y plus 6 is sine t? Those are question marks. Would that work? Some of you are nodding, some shaking, some doing the diagonal. Why won't that work? That seems like the direction I should be going, but why won't that work? Because if that's cos squared plus sine squared, can't really be 36, can it? If this were an ellipse, what would you do? If this were an ellipse, wouldn't you do it like this? I won't tell you what goes there.
This one, it's over 6 squared on the bottom.
Yeah, wouldn't I want the 36 down here? Is that correct, what I just wrote?
Yeah.
Oh, does that give you a different idea for your parameterization?
Mm-hmm.
So what do I want to use? X minus 2 over 6, maybe? Would that work?